So in this video, we're going to start our physical chemistry series lecture. Uh, and this is physical chemistry that you should expect at a undergraduate level. All right, so throughout all universities throughout the world, you should be able to see this sort of physical chemistry at the undergraduate, maybe towards the graduate level. Right, so the first thing we're going to talk about is the structure of signs. The structure of signs. And this says that we have observations, we have experiments, and we also have data, right? And we can do an induction and we make a hypothesis or some sort of theory or some sort of model equation, right? So that is a structure of science, and essentially from that we could create what we call a law. So with that being said, we say that theories, laws, etc., right? So all these other stuff, they cannot be proved. So cannot be proved, right? So there's no way we could prove them, but we can disapprove them. So they cannot be proved, but only be they can only be disproved, right? So that's a critical uh, concept that we need to get when we talk about the structure of science, right? Here we could actually quote Newton. So here's actually Isaac Newton on this subject, right? So he pretty much said essentially when I'm doing the quote, I'm not gonna write it out, but he pretty much says the best and safest way to to pretty much create a philosophy is to first diligently investigate the properties of things and establish them by experiment, right? And then to seek a hypothesis to explain them. So that was pretty much Isaac Newton on kind of theories, laws, etc., the structure of science. Now, the first one we need to talk about is what we call Boyle's law. And Boyle's law he actually found that gas volume decreases, right? So gas volume decreased as the pressure, and in this case I'm going to say P, the pressure P on the gas increased, right? So Boyle's law says that as the pressure goes up, the volume should decrease and vice versa, right? So let's look at an example. If I have, let's say I have a cylinder and I put a block, so this is my cylinder, here's the gas. And I put a 5 pound block on top. All right, and let's say this is 5 pound, right? In this case, we would have low pressure, so low P, and high volume. So the volume of the gas is pretty much high relative to the pressure versus something like this. Here's my gas, and now I have a 10-pound block on top. Right? So in this case, it would be high pressure in this case, a high P, but low volume. And that is Boyle's law in its entirety, essentially. So based on that, we could come up with a physical of a relationship, and so we say that this is measured, right? So if we measure several P's or several pressures and V's, we actually found that P is approximately equal to 1 over V, right? So that's the relationship that we need to keep in our head for Boyle's law. Now let's talk about thermodynamics. Transition to our lecture. Let's talk about thermodynamics. And thermo, the word thermo means heat. Dynamics, that means motion, right? So what is thermodynamics? We need to define what is thermodynamics before we actually go into depth about thermodynamics. So the first bullet point may be in the form of thermodynamics is a study of heat transfer. It's a study of heat transfer, right? That's what we define as thermodynamics. Now it also has empirical properties. So what we mean by empirical is that it's based on observation only. That's what empiricals mean, right? So it's based on observation only. Another thing that we could say about thermodynamics is that it's actually practical, right? So this is practical, right? So what do we mean? Something like an example of being practical is the foundation of industrial revolution 2 centuries ago. So like steam, engine, right? So examples may be steam, engines, right? Or even internal combustion engines, right? That's what we mean by thermodynamics being practical. And then obviously the last point would be something of relevance, right? So even in today, we use a lot of thermodynamics to explain whether it's a fridge in the house or, obviously cars driving, etc. All right, so let's talk about some terms and units. All right, so we're going to transition. Obviously, we've defined thermodynamics now, so uh, let's talk about definitions and units. So pressure. What is pressure? I mean, you guys are watching this video, and I'm sure that in order for you to come to a physical chemistry lecture, you should have taken General Chemistry 1, General Chemistry 2, Organic Chemistry 1, Organic. So you've pretty much have a strong background of chemistry thus far. And so we define pressure as the force per unit area. So we say pressure is the force per unit area, and we simply define this as F over A. So in other words, P is equal to the force over the area. Now, the units for pressure, we say Pascal. All right, so 1 Pascal or PA is equal to about 1 Newton meter squared. Right? This is also the same thing as 1. So this is also the same thing as 1 kilogram per meters times second squared. We also have a bar. So 1 bar is equal to about 10 to the 5th Pascal. We also have atmospheres, right? So 1 ATM is equal to 1.01325 times 10 to the 5th Pascal, right? And that is essentially equal to 1.01325 bar. So as physical chemists, we have to be cognizant of our units, right? So we've just talked about Pascal, we just talked about bar, we just talked about atmospheres and their equivalent relationships, right? We also are going to talk about torr, right? So 760 torr, right, is equal to 760 millimeters mercury. Right? So those are some of the units that we need to be familiar with when we introduce ourselves to physical chemistry. All right, let's revisit Boyle's law. Right? So Boyle's law, let's revisit it. So this is Boyle's law revisited. Remember, we say that the volume is proportional to 1 over the pressure. Right? That's the equation that we need to get in our head for Boyle's law. And this is equivalent to the fixed. We say that we have fixed amount of gas and the temperature is fixed. Right? So as soon as we start changing these parameters, then Boyle's law is kind of it's not useful anymore. So we say that we're looking at the volume, we're looking at the pressure, while there's a fixed amount of gas and there's a fixed amount of temperature, right? So these have to be fixed. And so essentially we're looking at some sort of perfect scenario, right? So we say V is proportional to 1 over P, or we could say that V is a constant times 1 over P. We could also say that PV is equal to a constant, right? The only thing we did a while ago was rearrange the equation. So we said that V can also equal to a constant times 1 over P. Or if we rearrange the equation, what we're really saying is a constant is equal to P times V. Or we can also say that P1 times V1 is equal to P2 times V2. And this is the formula that I'm pretty sure that most of you guys are familiar with respect to your general chemistry classes back in the days. Or in other words, we could also say that P is proportional to 1 over V. So that's Boyle's law. Now, what does a graph look like with respect to Boyle's law? And we're going to talk about isotherms. Right? So here we have a graph, pressure on the x-axis, and the y-axis is some sort of arbitrary unit, right? And we could see on a graph we say that this would be low temperature, and the solid line would represent high temp, right? So these are what we call isotherms, right? So with respect to Boyle's law, we should expect that the isotherm, again, for high temperature, we should expect uh, the graph to look in the form of a solid line in this case, and low temperature, the dashed line represented again by an arbitrary unit of y times p versus p on the x-axis. Right, so that's just a physical representation of what we're talking about when we talk about isotherms and Boyle's law. So let's look at an example. Let's look at an example of Boyle's law. So this is our example. Let's say at 25 degrees C, a 5.0 liter sample of nitrogen has a pressure P equal to, I'm going to put it right down here, equal to 10.0 bar. Right? My question is, what will be the volume? What will the volume be when the pressure drops to about 1.0 atmospheres. Right? So how would we solve this problem? Well, when you think about it, this is a Boyle's law when we said that, or equations. Let's write down what we know. So we know that P1 in this case is actually 10.0 bar, right? They've given us they've given us P1, right? So they ask what will the volume be, and they're asking for volume, so we know we have to solve for V. But what will the volume be when the pressure drops to 1 atmosphere, right? So we know that P1 is equal to 10 bar, and they've given us, I don't know if this is blocking, but P1 here is they've given us as 10 bar, and P2 is 1 atmospheres, right? So we know P2 is equal to 1.0 ATM or 1 atmospheres. And for the sake of easy calculations, we should recognize that we need to calculate our units in the same. We need to have our pressure in the same sort of unit. So this is 1.01325 bar, as you said before, with 1 atmosphere. Now V1, right? They've given us that, and that is actually 5.0 liters. So essentially what we're solving for is V2, and we don't know that, right? So rearrange an equation, V2 is equal to P1 times V1 divided by P2. And if you plug in your numbers, you should get about 49 liters, right? So that's an example of Boyle's law. Let's talk about Charles' law. Charles' law, or what we call Gay-Lussac's, Charles' law, what we call Gay-Lussac's law, is the idea that the volume is proportional to the temperature. So as soon as we increase the volume, the temperature should increase. Now, obviously, we got to make sure that we have a fixed amount of gas, and we also got to make sure that the pressure is fixed, right? So we have fixed amount of gas with respect to Charles' law, and we have fixed amount of pressure. So we define Charles' law as the volume is proportional to the temperature. So what does that mean? We could say or, right, V is proportional to T, or we could say that V is equal to a constant times T. Or we could say that V over T, just rearrange the equation, is equal to a constant. Or we could even say V1 over T1 is equal to V2 over T2. And this is a general chemistry formula that I'm pretty sure that most of you guys are familiar with. So if we look at a graph of Charles' law, similar to what we did for Boyle's law, we have temperature on the on the x-axis and some arbitrary value on the y-axis, and we could represent a solid line with low pressure, so low P, and a dotted line as high P. All right, so essentially on a graph, we should expect it to look like this. All right, so here's my low pressure with a dotted line, and I have high pressure with a solid line, and these are what we call isobars. Right? So Charles' law, interestingly, actually found, Charles' law found that all gases extrapolate to about negative 273.15 degrees C. All right, I'm sure you guys are familiar with this number, but this is where this number is coming from. And he pretty much developed the absolute temperature scale. All right. And if we remember from general chemistry class, we know that the absolute temperature scale is actually measured in kelvins. Right? And the unit for kelvins is just a big K. Right? So essentially our temperature in K, or kelvins, is equal to our temperature in degrees C plus 273.15. Right? So this is where our absolute temperature scale comes from, Charles' law. And we have to give credit for that. So we say that the temperature in kelvins is equal to temperature in degrees C plus 273.15. Right? So in that, we say that negative 273.15 C is called the absolute zero of temperature. So the absolute zero of temperature is what we defined as negative 273.15 degrees C. That is also called the absolute zero of temperature. Very important concept. Now let's talk about Avogadro's law. Let's talk about Avogadro's law. Avogadro is interestingly said that the volume is proportional to the number of moles. So this is different from Charles' law, which said that the volume was proportional to temperature. Here we're saying the volume is approximately proportional to the number of moles. And obviously we must have fixed temperature and fixed pressure. Right? Or we can say that the volume is equal to a constant times n. Or we could also say that the volume is equal of a volume over n is equal to a constant. And the only thing I did was just rearrange the equation. Or we could say that V1 over N1 is equal to V2 over N2. Right? So that is Avogadro's law. Right? So to recap what our laws that we talked about, we said that Boyle's law is equal to the volume. So this is approximate the volume is proportional to 1 over P. So that means as we increase the volume, the pressure decreases. When we talked about Charles' law, when we spoke about Charles' law, we said that the volume is proportional to the temperature, right? So, and we spoke about isotherms with respect to Boyle's law. We spoke about isobars with respect to Charles' law. And then the last one we spoke about was Avogadro's law, which says that the volume is proportional to n. Right? Now remember that each one of these laws, we have the pressure and depending on what we're talking about, usually the pressure and temperature fixed or the temperature and number of moles fixed, etc. Right? So combining all of these laws, so if we combine all of these three laws that we just spoke about, so combining all three laws, we actually obtain V is proportional to N times T over P. Or we could actually say, and let me move this up a little bit, or we can actually say that V is equal to a constant times N times T over P. Now, this constant, right, and this is what we're talking about, this constant has a special symbol. This constant has a special symbol called R, right? And we call it the ideal gas constant. Right? Now it is actually found experimentally to be the same. She actually found experimentally to be the same for all gases, which is actually interesting, right? So this R constant is actually found to be the same for all gases, and so R is equal to 8.314 joules times Kelvin inverse times the mole inverse. And that's simply saying joules divided by Kelvin times moles, right? Or we have a different unit for it. It's also equal to 0.08206, right? So this is 0.2086 liters times atmospheres times Kelvin inverse times mole inverse. We also have another number for it. This is 0.08314 liters times bar times Kelvin inverse mole inverse. Right? So these are all units for our ideal gas constants. So thus, we get the full formula, which is V is equal to R times NT over P. All right? So if we rearrange the equation, the equation, we get PV is equal to nRT. Right? And that's how we actually came up with the ideal gas law that you guys are familiar with in general chemistry. Now, some thoughts on the ideal gas law, right? All gases obey this law. Although we could say that they deviate. So all gases obey the law, although they deviate from it. So although they deviate from it at low temperatures, this is important. They deviate from it at low temperature and high pressures. Right? So the ideal gas law, we say that all gases must obey the ideal gas law. But again, if the pressure becomes too high or the temperature becomes too low, then the ideal gas law is kind of non-relevant at that point. We also must comment and say that a gas which obeys this law, we also must comment and say that a gas that obeys this law at all pressures and temperatures is called an ideal gas. All right. So again, we say that a gas law is kind of non-relevant when the temperatures become too low, the pressures become too high. But then again, we have to remember that any gas that obeys this law at all temperatures and pressure is what we call an ideal gas. Now, the last thing that we must comment on this is to say that an equation of this type, PV is equal to nRT, relating PVN and T is actually called an equation of state. So a very important concept, right? So an equation relating PVN and T is what we call an equation of state, right? So it's a very important concept. So let's look at an example. Let me move this up. Let's look at an example. Let's look at an example. So we're going to say, what's the volume? And I'm asking you in liters. What's the volume in liters of a 1.000 grams of nitrogen, right? What's the volume in liters of a 1.000 gram of nitrogen, right, at atmospheric pressure and room temperature, right? We know room temperature is about 77.0 degrees Fahrenheit, right? So we're asking for the volume in liters of a mass. We've given a mass of nitrogen at atmospheric pressure, and we asked about room temperature, about 77 degrees Fahrenheit, right? So this is a room temp. Well, if we rearrange the ideal gas law, V becomes nRT over P, right? Because we're asked for volume. So what is N? N is the number of moles, right? So we've given a mass of nitrogen in grams. So to get to a moles, and you guys should be familiar with this, we take the mass, which is 1.00, and pretty much divide by the molecular weight of nitrogen. Now remember that nitrogen is a gas, right? So really what we're doing is multiplying 14 times 2, and that gives us about 28.014 grams per mole, right? And that is essentially equal to 0.03570 moles of N2. Again, remember to use excess of this when we're thinking about significant figures. Now the temperature we said was 77.0 degrees Fahrenheit, right? And that is equal to about 25.0 degrees C. All right, so that is equal to about 25.0 degrees C. Now remember that because we're using the ideal gas law, we have to make sure that our units are right. And typically we do temperatures in Kelvin, right? So essentially we're going to take 25 degrees C because we spoke about how to calculate from to Kelvin. So we're going to take 25 degrees C plus 273.15 Kelvin. And that is equal to about 298. I'm sorry, plus 273.15. And that is equal to about 298.15 kelvins. So we have our moles, we have our temperature, we know the pressure is equal to 1.000 atmospheres exactly. And we know that R is equal to 0.08206 liters times atmospheres times Kelvin inverse, mole inverse. All right, so plugging into our formula for V, we get V is equal to number of moles. So this is 0.03570 times R, which is 0.08206 times 298.15, and that's all divided by our pressure, which is essentially 1 atmosphere exactly. And so you essentially get our volume to be about 0.08734 liters exactly. And note that the correct number of significant figures actually used in our formula, right? So that's our introduction lecture to physical chemistry, and check out the next video for lecture 2.